presolar grains are called presolar because they formed in other stars. So this here is not our sun, but it is a different star, and within this star the presolar grains formed. Now these grains were then transported after the end of the life cycle of this star into the interstellar material. And here the grains then accumulate together with other grains from other stars, other material, gas, and so on. Most of this material was destroyed, evaporated, and recondensed, but about 3% of really presolar material survived within the interstellar medium. Now this material could then be transported into the material and the protoplanetary disk from which our planets and solar system formed, and these grains were then incorporated within the protoplanetary disk into meteorites where we now find them. Here are a couple of examples how these presolar grains look like. And you can already see that these are rather small. So this is 1 micrometer here, this scale bar. This is silicon carbide, and this is maybe up to 2 micron diameter, which is, as I said, already rather large for a presolar grain. Second example is a nanodiamond. There are many nanodiamonds found, but these are very small. You can see here this has 25 microns, the scale bar, and actually these are many nanodiamonds. One is outlined, and we can actually see the individual carbon atoms or the layering of the carbon atoms within this 1 nanodiamond. Now then are 2 more examples of graphite and titanium carbide here. So the graphite is a couple of micrometers, as you can see here, and the titanium carbide are actually these tiny grains here. So these are very small again. And then there is corundum as one example. This is also around 1 micrometer. And finally, there's a silicate. So the latter two are looking at flat because they have been cut out with a focused ion beam, and this is why they get these flat surfaces here. So what you can see, and which is important, most presolar grains so far actually are not silicates. So silicon carbide, nanodiamonds, graphite, titanium carbide, and corundum, but also silicate. The reason for this is that previously meteorites have been, so if this is a meteorite, they have been dissolved in some acids, and the residues are non-dissolvable material, which is all the silicon carbide, titanium carbide, and so on. However, silicates are always dissolved during this procedure, and this is why silicates were basically destroyed during this procedure. But nowadays it is possible using TM or a secondary ion mass spectrometry, in situ mass spectrometry, to also find silicates, and there are also silicates that are presolar grains. Now this plot here shows the abundances of the various presolar grains. And down here, as you can see, is the scale in ppm. So this is from 10 to minus 9 to 10 to minus 2. So this is across 7 orders of magnitude in a log scale. Therefore, apparently, but 10 to minus 2, as you can see, this is not a lot of presolar grains within bulk meteorites. So nanodiamonds and silicates are the most abundant materials that are found in meteorites. Less abundant or almost oxides, and then silicon carbide, graphite, and something like silicon nitrides. Now what is also interesting here is that the origin of the presolar, the production side of the presolar grains are shown. So this here is supernovae. So many of these grains are produced in supernovae of the nanodiamonds, most of them. And silicates are produced in red giant stars, asymptotic giant branch stars, and again supernovae. So supernovae is one of the most main sources of presolar grains, as you can see here, because this is basically they produce all of these grains. And so this is the origin. This is origin and abundance of presolar grains, rather rare, coming from different stars, and this is how they look like and how abundant these are.